Hello Chem 1. Today we're going to take a look at solids, the four main types, and their properties. Let's get started. Before we get started with the four main types of solids, let's talk about some broader categories of solids. First of all, a solid is anything that has a definite volume and a definite shape. This means it can't be compressed. This means it's also not going to flow. A solid's not going to take on the shape of its container. It's going to be a rigid structure. That rigid structure can happen in a couple different ways. The first way is if it was a crystalline solid. This would be a repeating pattern that gives us a 3D structure of the object. Ionic compounds, covalent crystals, any type of crystal would be a crystalline solid. Other types of solids would be amorphous solids. These solids don't have a repeating pattern on the particle or molecular level. Sometimes these solids do have a little flexibility. Rubber, plastics would be examples of this, but glass would also be an example of an amorphous solid, which is one of the reasons we can see through it. It doesn't have a crystal structure that would refract light in all directions, like a diamond would. One property of solids is that they're typically more dense than their liquid counterparts. This is because the molecules or particles are closer together because of the stronger intermolecular forces and take up less space. As we've talked about before, this isn't the case for water. The way that water crystallizes leaves gaps in the crystal structure, which actually means that solid water is less dense than liquid water. This is why ice floats, icebergs float, because they're less dense than the liquid they're in. As we've already stated, solids can't be compressed, just like liquids can't be compressed, because there's not enough space in between those molecules to make them take up less volume. Another property that can help us take a look at solids and their intermolecular forces is melting point. This is when something changes from a solid to a liquid. Typically speaking, the stronger the attractive forces, the higher the melting point. It's going to take more energy to separate those particles. Alright, now that we've briefly talked about some properties of solids, we're going to get into four main types and how to identify them. Some of these you've already been introduced to in other sections, but some of them will be new. The first type of solid we're going to talk about is ionic solid. These solids are an arrangement of cations and anions that are in a repeating pattern that give us a 3D crystal structure. These ionic solids can be at different strengths depending on the size of the ion and the size of the charge that that ion has. Typically speaking, the higher the charge, the stronger the bond, and the smaller the ion, the stronger the bond. These crystal structures can be very strong, and therefore most ionic salts have really high melting points. Ionic solids also have positive and negative cations, or a positive and negative end. Because of this, they dissolve very well in other polar substances, like water. Salts always dissolve very well in water. Ionic substances typically won't dissolve in nonpolar solvents. Remember, like dissolves like. Also, because of the positive and negative ions in an ionic compound, when they're dissolved, you'll also be able to transfer electrons or conduct electricity through that substance. If they're not dissolved though, if they're still in the crystal structure, they won't be able to conduct heat and electricity as well. All ionic solids are solid at room temperature. They have a very low volatility because there's great strength in between those particles holding them together. Any ionic substance that we've talked about this year would be an example of an ionic solid. We've used many of them in lab, any cation and anion pair. The second type of solid we're going to talk about is a molecular or covalent solid. These substances aren't repeating patterns. They're discrete molecules. They stand alone by themselves. Think H2O, CO2, anything that's covalently bonded that can be its own individual molecule. So within a large sample of these molecules, the things that are holding them together aren't bonds, like with an ionic compound. They're intermolecular forces. And we know that intermolecular forces aren't as strong as bonds. Because of this, molecular solids tend to have low melting points. They're very easy to heat up and separate. Most molecular solids are insoluble in water unless they're polar, like water. But many of them, because they're nonpolar, will dissolve in other nonpolar solvents. They're typically non-conductors in the solid form, and some can conduct if they're dissolved into water. Most molecular compounds are solid at room temperature. If they are liquid at room temperature, they will be volatile because of those weak intermolecular forces. Anything that's a standalone molecule like H2O or ammonia, NH3, or CO2, those are molecular solids. Our third type of solid is what happens when you have covalent bonds, But instead of making a standalone molecule, it's going to make a network of those bonds. This creates very strong networks. Their melting points are going to be very high because of the strong network that they are providing. Remember, since they're bonds, they're not being held together by intermolecular forces, but intramolecular forces, bonds that are very strong. Because of the strength of those intramolecular bonds, they are not soluble in polar or nonpolar substances. Most of them are very poor conductors because all of their electrons are used up in those intramolecular bonds. There are certain types that can be conductive, like graphite, but most are not. All of these networks are solid at room temperature and are very non-volatile, once again, because they're held together by strong covalent bonds. There are only 8 network covalent solids. Carbon makes 2, diamond and graphite. Then you can have silicon, silicon dioxide, which is quartz, germanium, red phosphorus, silicon carbide, and boron nitride. Those are the 8 that you need to know. Anytime you would see one of those 8, you would immediately identify it as a covalent network solid. When we get to identifying the different types of solids, the first solid you should eliminate is this one, because it's got to be one of the 8, and if it's not, you know it can't be a covalent network solid. Our last type of solid is metallic. We've talked about metallic bonding briefly. This is when positive cations are surrounded by a sea of delocalized electrons that can move freely throughout the structure. Just like ionic bonds, the strength of a metallic bond is based on the size of the ion, smaller the stronger, and the charge of the ion. More charge, more strength. Melting point in metals varies significantly because of all the different types of metal ions we have. Mercury's melting point is -40, while tungsten's melting point is over 3,000 degrees Celsius. It all comes down to the strength of that metallic bond. So things typically to the left side of the periodic table have weaker metallic bonds, and a lot of times they'll melt sooner, and they're often easier to cut and break, like potassium you can cut with a knife. Where as you start moving right toward the metalloid line, the charge goes up and the size of the ion goes down, which means they become stronger. Chromium, iron, aluminum, these types of metals. Metallic solids are not soluble in water and they're not soluble in nonpolar substances. But they are very conductive because they have free electrons in their bonds that can transfer that charge from a positive to a negative. All metals are solid at room temperature except for mercury. And therefore mercury is the only one that has any type of volatility. Other examples of metals are anything on the left side of that metalloid line on the periodic table. One of the things we want you to be able to do in this section is classify these solids, where we give you something and say, what is this? And these 3 questions are kind of a way to guide you to figure out what type of solid you're looking at. The first thing you're going to ask is, does it contain a metal? If it contains a metal, it can only be an ionic solid or a metallic solid. Ionic solids will always be a pair of a metal and a nonmetal, or a cation and an anion. And then a metallic solid will just be a metal by itself. If there's no metal contained, that means it's covalently bonded. Remember, covalent bonds are made from nonmetals only. So if it's covalently bonded, it can be one of the 8 covalent network solids, or it's going to be a molecule. So let's try this out. The first thing we have here is SiH4. We know that silicon is a metalloid, it's not a metal. So the question is SiH4 one of the 8 or is this a molecule? If you need to, you can go back to those covalent network solids and you can see that this is not one of the 8, meaning this is just a molecular solid. Next we have NaCl. Na is a metal, and in this case it's paired with an anion, meaning that this is ionic. The next one we have here is C6H12O6. There is no metal present, and this is not one of the 8 covalent network solids. So once again, this is molecular. Then we just have Cu. It's a metal by itself, so it's metallic. Those are probably the easiest ones to identify. Potassium down here is by itself. It's a metallic solid. Then we have SiO2. There's no metal present here. And if we look, this is one of the covalent network solids on our list of 8. So you could just write covalent network. Then we have boron nitride. This is another one of the 8 covalent network solids. So we could write covalent network. And then finally we have MgO. Mg is a cation, O is an anion. This is an ionic compound. This will become easier the more you practice this process. The last thing we want to show you here today is just a continuum of strength. Typically speaking, molecular are the weakest. They're going to have the lowest melting points. They're going to be the most volatile. And then over here, the covalent network are going to be the strongest, diamond, quartz. Ionic will be next, and then metallic. There are some metallic ones that are stronger than ionic, but because of the wide variety within metallic in terms of those intermolecular forces, we put them closer to the left or closer to the weaker side. You may have questions in the future asking you to put certain types of solids in order based on strength, and this can be really helpful for that. Hopefully now you have a better understanding of solids and the different types and their properties. Keep up the good work. We'll see you soon.